Topic 7.2 is a discussion of a secondary air pollutant called photochemical smog. And photochemical smog is a reaction that takes place when heat and the energy from sunlight causes a reaction between two primary pollutants, nitrogen oxides and volatile organic compounds. And in these conditions, it produces secondary pollutants that include several different substances: ozone, O3, nitric acid, PANs, and aldehydes. And so we can see in this model sort of the chemical reactions that take place to form some of these compounds. So if we look at the top, this is under conditions in which you don't have VOCs. So in normal conditions, nitrogen dioxide is released from anthropogenic sources like vehicles mostly. And then the ultraviolet radiation from the sunlight causes the breakdown. One of those oxygen atoms is stripped off of the nitrogen dioxide, and it combines with oxygen, and that forms O3. O3 is ozone. And typically what happens when the sun then sets or when solar energy is reduced, some of that ozone, the majority of it then, the reaction reverses, and the ozone combines with the nitrogen oxide, and oxygen gets stripped off to form more NO2, and then oxygen gas is released. So under these conditions, we generally have a buildup of ozone during the daylight hours and then a drop in the evening hours. So that's in a condition when you don't have another pollutant called VOCs. But what happens in certain areas when you have large amounts of these volatile organic compounds is shown at the bottom of this model. So the same process takes place. Nitrogen dioxide combines and oxygen gets stripped off to form ozone. But when you have VOCs also present in the air, the VOCs combine with the nitrogen oxide and they form the other photochemical pollutants, the photochemical oxidants. And the mixture of those photochemical oxidants and the ozone is what we call photochemical smog. And so the factors that increase the production of this photochemical smog are when you have high levels of heat and sunlight, and then you have these VOCs and hydrocarbons present. So we typically see photochemical smog forming in areas where you have a lot of motor vehicle traffic, sunny areas during times of high temperature. Those are the conditions in which we can see the formation of this photochemical smog. And the effects of photochemical smog are several. In terms of human health, photochemical smog can exacerbate respiratory illnesses such as asthma or emphysema, can cause eye irritation. It also interferes with plant growth, so it has effects on ecosystems as well. Oftentimes, people that live in areas where photochemical smog is often an issue, they may check the ozone levels on their weather apps before going out and exercises, and sometimes you could have warnings that people should not be outside exercising during times when the smog is building up. So we can see just sort of in this next graph, we can see another model that is a little bit simpler. But again, it shows the nitrogen dioxide that's released from car exhaust and other sources combining. One of the oxygens gets stripped off, okay, to form nitric oxide and then ozone. And those aldehydes, those hydrocarbons and PANs are what form the photochemical smog. And we can see here in this graph, this shows over time what we typically see in areas where we have urban photochemical smog. In the morning hours when there's a lot of commuting, there's high levels of nitrogen dioxide. As the sun comes out and it warms up, then that gets converted through the process we just talked about into O3, ozone, and then we often see the decomposition later in the evening. There's a couple instances. So there's another, smog is just a portmanteau of smoke and fog. And so we were just talking in the previous slides about photochemical smog. There are other types of smog as well. This picture of this London police officer comes from what was sometimes called the Great Smog of 1952. In London, conditions were so that it was really cold, so there were people burning lots of coal to heat their homes, and there was also power plants in London powered by coal. And it was relatively low quality coal that released a lot of soot and sulfur compounds. And in 1952 was December, it was a cold period. This combined with temperature inversion, which we'll be talking about, worked to trap this smog close to the surface. It lasted for 4 or 5 days, and it ended up resulting in over 100,000 people becoming ill from inhaling that smog. The smog was so dense that in the middle of the day, they needed to turn on the lights of cars. People were advised not to go outside. And so the estimates are that about 10,000 people in London died from respiratory illnesses that were caused by the smog. We also know that photochemical smog is often present in areas where you have a lot of combustion, especially motor vehicle combustion, and geographic features also can make this worse. Cities that are in valleys where the smog tends to settle can have an issue. So Los Angeles is a city that has smog problems oftentimes. Shanghai, China also has some serious smog issues at different times of the year.